All right, guys, here we go. 1-9, patterns, equations, and graphs. After this lesson, I will be able to use tables, graphs, and rules or equations to describe relationships. So here we go. Tables, graphs, rules, otherwise known as tables, graphs, equations. Here we go. The table below shows the relationship between the number of kites in an arrangement and the total number of ribbons on the kite's tails. Describe the pattern in the table. How many kites could you make with 275 ribbons? So describe the pattern in the table. I'm just going to kind of get rid of those pictures a little bit and make it a little bit more of a traditional looking table. I got the kites on the top. I got the ribbons on the bottom. One kite gives me 5 ribbons, 2 kites, 10 ribbons, 3 kites, 15, etc. One kite, 5 ribbons, 2 kites, 10 ribbons, 3 kites, 15. All right, so I can see each time I'm going up by 5 ribbons. So the number of ribbons equals the number of kites times 5. 4 times 5 is 20. 3 times 5 is 15. Or you could say the other way, you could say the number of kites is the number of ribbons divided by 5. 10 divided by 5 is 2. 15 divided by 5 is 3. Okay, so either one of those would be great. If there's 275 ribbons, well, the number of kites equals the number of ribbons divided by 5. If there's 275 ribbons, 275 divided by 5 gives me 55 kites. So you can see the table kind of helps me build the equation, and then from the equation it's easy to answer the question. All right? Great. So we got 2 essential understandings here. We can describe a pattern using words, an equation, or a graph. And then the big one is sometimes the value of one quantity can be found if you know the value of another. You can represent the relationship between quantities in different ways, including tables, equations, and graphs. All right, we can use an equation with 2 variables to represent the relationship between 2 varying quantities. A solution of an equation with 2 variables is any ordered pair that makes the equation true. Okay, so whenever they ask me, is it a solution, all I'm going to do is replace any x's with the first number in the ordered pair and any y's with the second, and then I just decide, did it make a true statement? If the answer is yes, it is a true statement, well then that point is a solution to the equation. So let's take a look. Identifying solutions of a 2-variable equation. Remember, replace the x with the first value in the ordered pair, the y with the second. Decide, did it make a true statement? If it's yes, well then the point is a solution. If it's no, then the point is not a solution. So here we go. Is 310 a solution to the equation y equals 4x? So this is the point, a location on a grid. Remember, it's always alphabetical order. So the 3 is the x, the 10 is the y. So all I'm going to do is take the 3 and plug it in for x. I'm going to take the 10, plug it in for y, and see if I created a true statement. So if I take the 10 for the y and the 3 for the x, I would wind up with 10 equals 4 times 3. Well, 4 times 3 is 12. So I came up with 10, which is not equal to 12. So therefore, I did not get a true statement. So 310 is not a solution. Let's take a look at another one. Is negative 4, 7 a solution to y equals negative 3x minus 5? So remember, the first coordinate is always the x. The second one is always the y. So I take the negative 4, plug it in for x, take the 7, plug it in for y, try to see if I made a true statement. So if I plug those in, I'd wind up with 7 for y equals negative 3. That stays negative 3. Take the negative 4, plug it in for the x. So negative 3 times negative 4 minus 5. Negative 3 times negative 4 makes a positive 12. Positive 12 minus 5 makes 7. So I came up with a statement that says 7 equals 7. That's obviously a true statement. So negative 4, 7 is a solution because it gave me a true statement when I plugged it in. Okay? Here we go. We can represent the relationship between 2 variables in several different ways. We can do a table. We can do an equation or a rule. And we can do a graph. All right, so those are our big 3. Table, rule, or equation, and a graph. All right, here we go. Both Carrie and her sister, Kim, were born on October 25th, but Kim was born 2 years before Carrie. How can you represent the relationship between Carrie's age and Kim's age in different ways? Well, what do we know? We know that Kim was born 2 years after Carrie, or Carrie was born 2 years before Kim. All right? So if Carrie was 1, well, then Kim is 3. If Carrie's 2, well, then Kim is 4, because Kim is always 2 years older than Carrie. If Carrie was 3, well, then Kim's 5, etc., etc. Okay, and we can extend the table as far as we want. Okay, so Kim is always 2 years older than Carrie. All right, so that's the table. Pretty simple. All right, let's look at some other things that we can do. So here's my table again. Okay, now we're just going to take those points and we're going to plot them on a grid. All right, so I'm going to put Carrie's age on the x-axis down below. I'm going to put Kim's age on the y-axis along that vertical axis. Make sure you label your axes. So Carrie's age, Kim's age, and then all I'm going to do is take these points and put them on there. So anytime I plot a point, just look and see where your axes are. So Carrie's age is on the bottom. So she's 1. Kim is 3. So 1, 3 would be my first point, which would be right there. My next point. Carrie's 2. Kim's 4. 2, 4. 3, 5. 4, 6. 5, 7. And you can keep going forever and ever and ever, and you would see that this line would represent those dots. Okay, this is what we call a linear equation because it can be represented with a line. All right, let's take a look at an equation or a rule. Well, if we let C be Carrie's age and K be Kim's age, well, what do we know? We know that Kim's age is Carrie's age plus 2. Kim is 2 years older than Carrie. So Carrie plus 2 would make Kim. So using our symbols, just to cut down on the words that we need to write, K equals C plus 2. All right. Problem number 2. Will runs 6 laps before Megan joins him on the track. They run together at the same pace. Represent the relationship between the number of laps Will runs and the number of laps Megan runs with a table, a graph, and a rule. All right. So what do we know? We know that Will has already run 6 laps when Megan gets there. So if we're looking at the total number of laps, Will's laps will be 6 more than Megan's. All right. So when Will has run 6, Megan has yet to run any. When Will runs 7, Megan has run 1. Right? Will's are always 6 more than Megan's. So 8, Megan's would be 2. 9, Megan's would be 3. And we can extend the table as long as we want. Okay? Good. So just go back to the table. Okay, now, so I did the table. That's easy. So now if we go to plot those points onto the grid, we just need to know which axes we want to label with which one. And as long as you label it, it really doesn't matter which one you pick. So Will on the bottom in my picture, you could have Will on the side. As long as it's labeled and you plot the points accordingly, then everything's fine. So Will's 6 when Megan is 0. So 6 for Will, 0 for Megan would be right there. 7 for Will, 1 for Megan would be right there. 8 for Will, 2 for Megan would be right there. And you can continue and you can see the pattern that would look like that. Okay? Great. As a rule or an equation, well, what do we know? If we let W be Will's laps and M be Megan's laps, well, Megan's laps equals Will's laps minus 6. Right? She always has 6 less than Megan, than Will. Megan always has 6 less than Will. So using your symbols, M equals W minus 6. You could also have the equation Will equals Megan plus 6. That would also be a good equation. Will's laps are Megan's laps plus 6 more. So W equals M plus 6 would also be an equation. Okay? Now lots of times we take these things and then we try to answer some questions with them. So the process of reaching a conclusion based on an observed pattern is called inductive reasoning. And we use inductive reasoning to predict values. So here we go. A table shows the relationship between the number of blue tiles and the total number of tiles in each figure. Extend the pattern. What is the total number of tiles in a pattern with 8 blue tiles? So here's the first picture. There's 1 blue in this picture, and there are 9 total. So 1 blue, 9 total. In this picture here, there are 2 blues, and there are 18 total. This picture here, there's 3 blues, there's 27 total. Okay? So I got a nice little table there. So my rule or equation, if I just go right from the table, all right, let's take a look. If x is the number of blue tiles and y is the total number of tiles, well, then the total number of tiles equals the number of blue tiles times 9. 1 times 9 is 9. 2 times 9 is 18. 3 times 9 is 27, and continue. Okay, so from the table, we were able to write an equation. Okay, if we want to abbreviate that equation, y equals 9x. Y is the total number of tiles, x is the number of blue tiles. Okay, let's take a look at a picture. So I'm going to put the blue tiles on the bottom. All right, now notice your numbers here are a little crazy. You know, it's going all the way 9, 18, 27. Okay, so I'm going to scale my axes accordingly. My blue tiles I'm putting on the bottom, so I'm just going to go one at a time. The total number of tiles I'm going to go on the left side, and I'm going to count by 9s. Okay, make sure each interval, each box counts the same amount. So from there to there is 9. So from the same space, from here to here, this line to this line has to count as the same amount of numbers. So from here to here was 9, another 9, another 9, another 9, etc. So now just using the table, you can just plot the points. 1, 9, 2, 18, 3, 27, 4, 36, etc. Okay? Now before you go and connect those dots, let's think about it a little bit. We should not connect those dots because in this case, there must be a whole number of tiles. I can't have 5.2 tiles. Okay, so I only want the dots. Okay, now what we will do, whenever I have a graph just made up of dots, they call that a discrete graph. All right, if we were to connect those dots, like in the 2 previous examples, we call that a continuous graph, something you could draw without having to lift up your pencil. Okay, so we can represent it with, normally we would just use like a dashed line to kind of help us see any values that are not in the table. Okay, so this is the same problem. We're just going to go answer the question. So it says, what is the total number of tiles in a pattern with 8 blue tiles? Well, we could extend the table, or we could use our rule. So our rule was the total tiles equals the number of blues times 9. So again, we let x be the number of blues. We let y be the total. So y equals 9x. And we know that x, the number of blue tiles, is supposed to be 8. Pattern with 8 blue tiles. So I just let that be 8. And you can see that y is 72. All right. Now, if we look at our picture, this is our beautiful picture that we made before. We wanted to know when there were 8 blue tiles. So if I just go down here to 8 blue tiles, and then I go up and I see where I hit my line, well, I hit my line right here. Okay? So that point, 8 blue tiles, and if I look over to the left, I can see that that hits at 72. So whether you use the equation, whether you use the graph, whether you were to extend the table and go 654, 763, 872, any of those work, are always going to give you the same answer. So the table, the graph, the rule, they're all going to get you to the same spot. Okay? That's it. I'll see you next time. Peace.